All right, our next talk is sampling graphs without forbidden subgraphs and unbalanced expanders with negligible error. The work is by Benny Applebaum and Eliran Kachlon, and Eliran will give the talk.
Thank you. Hi, everyone. My name is Eliran, and I will present a joint work with Benny. We will start by talking about forbidden subgraphs. Then we will talk about sampling graphs without forbidden subgraphs. And finally, about unbalanced expanders with negligible error. So our motivation to this work comes from two different directions. The first one is generating a graph G with no small subgraph H. And many combinatorial objects can be described in this way. For example, a graph with no short cycles, a graph with no small cliques, expander graph that avoid the small non-expanding sets, and error-correcting codes that avoid stopping sets. So let's see an example. So in this example, this is our bed graph H, and this is the graph G. And note that H is a subgraph of G. And I want to emphasize that when I say subgraph, I do not mean induced subgraph, but only subgraph, as you can see in the picture. And finally, sometimes the best-known constructions of such objects are probabilistic constructions, in which we simply take G in uniform, and the properties that we want hold with high probability. So let's see an example. Again, we are given a bed graph H of size T, and we want to generate a H-free graph G that has n vertices and m edges. And when I say that the size of the graph is T, I mean that the number of edges is T, and you should think of T as a large constant. So the first method that we can try is the rejected sampling algorithm. So for example, this is the bed graph H, and those are the vertices of G. And we simply sample the graph G uniformly at random from all graphs with n vertices and m edges, and start looking for H in G. And in this case, we found that H is a subgraph of G, so we reject this graph, we sample another graph, and so on, until we found a good graph G. And if most graph G are good, that is, they do not contain H as a subgraph, then the running time will be something like n to the number of vertices of H. And since T is the number of edges, this is something like n to the square root of T. Now, since T is a large constant, and it appears in the exponent of n, this is not a nice term. What we would have liked is a running time of f of t, where f is some function of t, times n to the c, where c is a constant that does not depend on c, that does not depend on t. So this method seems to fail, and indeed the exponential time hypothesis implies that general testing for subgraphs cannot be done in this time. Okay, so this was the first try, and our second try might be simply to sample a graph G and then return it. And if most graphs are good, then with high probability, our graph will be good. The problem with this method is that the error probability is too large. So I claim that this is a lower bound, so let's see why. Fix any vertices in which H can appear. So in this case, for example, those three vertices. And give number to the edges of H, 1, 2, and 3, and to the possible numbers of G. Okay, so the possibility that the first edge of H appears as edge number 1 there is something like m over n squared, and that the second edge of H appears as edge number 2 is m minus 1 over n squared, and so on. And since T is a constant, this is at least 1 over poly n. Again, what we would have liked is an error which is negligible in n, which means that it goes to 0 faster than any inverse polynomial. So this method is not good enough for us either. So we've seen that we either have problems with the running time or with the error probability. So this brings us to the first motivating problem, which is to efficiently generate a graph G, which is H-free, with negligible error or zero error. And by zero error, I mean that the construction algorithm succeeds with high probability, and whenever it fails, it outputs some special symbol. Okay, and I want to emphasize that this problem focuses on the error probability of the construction, which is unlike the de-randomization literature that usually emphasizes the distinction between probabilistic constructions and deterministic constructions. Okay, so far we So far, we tolerated randomness as long as the error probability was small. But in fact, randomness is not necessarily a bug. It might also be a feature. So the second problem is to generate a typical H-free graph of a given density. And a little bit more formally, we want to sample graph G from some pseudo-random distribution conditioned on being H-free. So this combination of requirements may arise, for example, if we want to understand the behavior of H-free systems, or if the analysis of the algorithm that needs the graph G depends on G being both H-free and a pseudo-random or random graph. Okay, so those are our motivating problems. And let's go to the main results. So the main result is essentially two efficient algorithms, a sampler and a tester. So this is the sampler. It receives the number of vertices that we want G to have, the number of edges of G, and random coins. And it outputs a graph G. And G is k-wise independent. And by k-wise independent, I mean that every set of k edges are uniformly distributed. So this is the sampler, and we also have a tester. The tester receives the same random coins as the sampler. And it also receives the bad subgraph H. And it outputs yes if G is H-free, and it outputs no if G is not H-free. Okay, so in this case, we've seen that G is not H-free. Okay, so let's talk about the complexity of the sampler and tester. So the sampler is efficient in N and M, which means that it runs in time polynomial in N and M. The parameter K, the independence parameter, is greater than any polylogarithmic term in N. But it is smaller than n to the literal of 1, which means that it is smaller than n to the epsilon for every positive epsilon. Okay, but previous works shows that in this regime, k-wise independent is indeed a good model of pseudo-randomness. Okay, so this is about the complexity of the sampler. And the tester runs in time which we called efficient previously. That is f of t, where f is some function of t, times n to the c, where c is independent of t. Okay, this means that for every constant t, the running time is polynomial in n, and the exponent of n does not depend on t. And in fact, we can even take t to be a super constant and very slowly growing function and still get a polynomial time. Okay, so this is the main result. And there are two remarks here. First, the result generalizes to D regular hypergraphs, which we can think of as bipartite graphs. And there is also a succinct version in which the size of the representation of the graph G is polylogarithmic in N. Okay, and the notion of succinctness is due to GGN. And we have some corollaries from the main theorem. So the first one is that if G is H-free with noticeable probability of 1 over poly n, that is that there are some good graphs, and we can, in polynomial time, we can find such a one. Then we have a zero-error construction of k-wise independent H-free graphs. And in fact, under some de-randomization assumptions, we even have explicit constructions. And the second point is that the sampler and tester framework allows us to exclude families of bad graphs H. So in this example, we can first test for the 4 cycle, and then for the click, and then for this graph, and so on, and make sure that G does not contain any of them. Okay. So using the sampler and tester, we can construct an unbalanced expander. So an unbalanced expander is simply a bipartite graph with n vertices on the lower side here, and for example, n squared vertices on the other side. And the upper side is D regular, which then we want the D to be a constant. Okay, and the property that we require from the graph is that every set of vertices from the upper side, which is not too large, will have many neighbors on the other side. So in this case, we say that the set has a good expansion. And the previous works on the constructions of unbalanced expanders either have a constant D, but only linearly many vertices on the upper side, or they have polynomially many vertices on the upper side, but D is super constant, and we want D to be constant, and and have polynomially many vertices on the upper side. Okay, so at a high level, the main idea of the construction of negligible-error unbalanced expanders is to combine two graphs. The first graph has a good expansion for very small sets, and it can be generated using our sampler and tester. And the second graph has good expansion for medium-sized sets, and it can be simply taken at random. And we can show that such a graph is good with all but negligible probability. And by combining the two graphs, we get a graph which is good for all sets, for all sizes of sets. Okay, so using the unbalanced expander, we also get a construction of batch codes, of high-rate LDPC codes, and of local randomness extractors. And finally, assuming Gordreier's one-way function assumption, we also get a locally computable PRG with polynomial stretch. And so there has been a lot of work in this field. And Benny Applebaum showed that based on this assumption, we can get a local weak PRG with polynomial stretch. And by weak, I mean that the error is 1 over polyn. And we show how to transform this weak PRG to a strong PRG with negligible error, and still maintain the locality property and the polynomial stretch. Okay, the main problem with all of those constructions is that the error is, it is indeed negligible, but it is not as low as we would have liked. Okay, so I will say a few words about the construction. The main idea of the construction is to design a k-wise independent distribution which allows efficient testing for small subgraphs. That is, we specifically designed the distribution so that testing would be easy. Okay, so let's see how to sample a graph with n vertices and n edges, which is k-wise independent. So I take n to be a prime, and we represent every vertex as a field element. So those are the vertices. And each edge is also represented by a field element. So those are the edges. And the edges are defined by two polynomials, a and b, which are univariate random polynomials of degree k. Okay, so the source of each edge, h, is a of h, and the target of h is b of h. So if, for example, a of h1 equals 3 and b of h1 equals 4, then h1 goes from 3 to 4. And if a of h2 equals 1 and b of h2 equals 2, then h2 goes from 1 to 2, and so on. So indeed, we have n vertices and n edges. And the reason that the graph is k-wise independent is that if we take a random degree k polynomial and look at its evaluation on k distinct points, then the evaluations are uniformly distributed. So this is the sampling algorithm. And let me describe the testing algorithm. So this is the tester, and the main idea is to reduce the testing for subgraphs to solving polynomial equations. So let me show you how to test, for example, for a 4 cycle. So this is the bed subgraph H. And the main observation is that if such a graph H exists in the graph that we sample, then there are 4 distinct edges, H1 to H4, such that those equation holds. That is, the source of the target of H1 equals to the source of H2. The target of H2 equals to the source of H3, and so on. So what we do is simply to take 4 variables, x1 to x4, 1 to each edge, and construct this first system of equations, which again requires that the target of x1 will be the source of x2, the target of x2 will be the source of x3, and so on. And indeed, if a 4 cycle exists in the graph, then this system of equations has a solution. But it turns out that the other direction is not true. That is, this system of equation may have a solution even though a 4 cycle does not exist in the graph. So let's see why. So this is not enough. And the equations are also solved by 2 cycles. So again, this is the bed graph H. And assume that the graph G that we sample contains 2 cycles. And so we have 2 edges, H1 and H2, that are both field elements. And we can set simply x1 equals x3 equals h1, and x2 equals x4 equals h2. And note that the target of x1 is the source of x2, and the target of x2 is the source of x3, and so on. So the first system of equations is not enough. And what we actually need is the distinctness gadget that will make sure that all the x's are distinct. And in order to do so, we add some additional variables, the y's, y0 to y3, and we think of them as the coefficients of a polynomial p. Okay, and we simply require that the evaluations of p on each of the x's are distinct. So we require that the evaluation of p on x1 will be 1, and the evaluation of p on x2 will be 2, and so on, where 1, 2, 3, and 4 are 4 distinct field elements. And indeed, if the first system of equations has a solution in which all the x's are distinct, then such a polynomial exists and can be found by using interpolation. And for the other direction, for any assignment to the x's, if such a polynomial exists, then the x's are necessarily distinct because we have a polynomial that has distinct evaluation on those points. So this is our distinctness gadget. And there are some more technicalities. So in the general case, we also need a distinctness gadget for the vertices and not only for the edges. And we solve the equation using Kayang's algorithm. OK, so to conclude, we've seen the sampler-tester framework. We designed an easy-to-test k-ways independent distribution, which allows testing, even though in the general case, testing may be hard. We've seen the negligible-error construction of unbalanced expanders. And we've seen a transformation that preserves the locality from a weak PRG to a strong PRG. And the future work may include new randomized constructions that improve the parameters of this work. And there is also an open problem on whether this can be done in the uniform distribution. That is, if we can take a uniform graph and make sure that it is H-free. Okay, and we show some barriers in the paper. Okay, that's it.
Questions?
It's about half the degree, a little bit less than half the degree. It's n to some constant. Could you please repeat the question?
Do you get any kind of structure on how typical H-free graphs on images look like here?
I didn't understand the question.
So you're sampling the...
Yeah, I don't.
Sorry. So in the sampling H-free graphs, do you get any kind of structure on how H-free graphs on M edges typically look like?
In the sampler?
Yeah, in the sampling H-free graphs. So when you're sampling H-free graphs, do you also get any kind of handle on how they look like?
No, nothing more than the k was independent.
I'm sorry?
Nothing more than the k was independence.
Any other questions? All right, let's thank our speaker again.
Thank you.